So to talk about performance, we need an airplane drag model. So we've talked about how we calculate the drag for a wing. Airfoils, you get the data straight from the charts. If it's flying fast, you have to add wave drag. If it's a finite wing, then you have to add induced drag. So that starts telling us how we can calculate the total drag of the airplane. So we'll have the profile drag, which, remember, this is from the airfoil data that you look up in the back. And then we have to add the induced drag. And then you have to add that, so that's the finite wing effect. And then if it's flying fast, then you throw in your estimate for wave drag. But then it's an airplane, so we got to add in the drag of the horizontal tail and the drag of the vertical tail. All of those are flying surfaces, they're wings, little tiny wings or bigger. And then you got to add in the fuselage. You keep going, everything. If you have an antenna, you have to add the drag of the antenna. So in this class, we don't have enough information on the airplane to build this whole up. We don't have enough time either. We'll do more of this in 514. But we will be given a drag polar for the airplane. That is the models for all of this stuff added all together and collected into one formula. If you remember, the induced drag was of the form CL squared over pi E AR. So some of this drag is going to vary with the lift squared. And then some of this is just constant regardless of what the lift is, like the profile drag. So you'll see terms in this total drag model that have both of those, either a constant value or it depends on CL squared. So our drag model for the airplane, now we're talking the total airplane, everything added together. And notice it depends on CL squared and the aspect ratio, just like the induced drag. But it has this E hat thing in it that includes everything added together. And then the CD0 has all of the constant terms added together. And this E hat thing is similar to the Oswald efficiency factor, E. But sorry, this is the span efficiency factor. This is called the Oswald efficiency factor, and it's really just a composite of all the efficiency factors of the entire airplane. So this thing is called the Oswald efficiency. And it will be given to us. Again, because in this class, we don't have the time or the tools to build up this drag model from scratch. So for performance calculation, we'll be given CD0 and E hat, and we'll know the aspect ratio.
That right there, the top one, go with the normal efficiency, what's that again?
This is just, remember, that's the formula for CDI, the induced drag of a finite wing, just the wing, yeah. This whole thing is for the whole airplane. Now, if you look at this, if we plot CD versus CL, it's going to look like a parabola because it's squared. So these plots, or this formula, looks a lot like the drag that you see in the plots for the airfoils, because it's airfoil data added up. And so these plots in this formula look like this. There's the squared behavior. And then the minimum here is that CD 0. So sometimes, for some airplanes, this should be capital L, sorry. Sometimes that bottom is shifted over. Say it may be over here like this. And so we have to adjust the formula, because when CL is 0, that's where the minimum occurs in this formula. So sometimes you'll see a formula with that shift in it. And it's just like shifting f of x. You add something to x inside the formula. So in this case, it looks like this, and this is that minimum drag location. So it's just a formula of that same curve shifted over to the right or shifted to the left. But either way, we'll be given this formula for our calculations. All right, I'm going to erase this, and we're going to draw a free body diagram of the airplane now. And I want you guys to carefully, I'm going to walk through it step by step and tell you what to draw. I want you to draw it pretty big on a piece of paper. As you know from dynamics and statics, free body diagrams are how you do dynamics and statics. We're going to do the dynamics and statics of an airplane. So we're going to draw a free body diagram, which means we're going to put all the forces on it. So are you guys caught up? Are we good on copying this down? Okay, step 1. Draw a line all the way across the page. And that's a horizontal line. So this is like the horizon. So it's horizontal. And then draw an airplane. Pick a point right in the middle. And around that, draw an airplane pointed up. Like this. And then draw a wing here. And then draw a chord line through the tip and the tail of the wing. So this is a chord. And even though it looks like an airfoil, this is the whole wing. We just can't see the other parts of it. And it could be swept back and all kinds of things. But for now, you can just think of it as a rectangular wing represented by that picture. Okay, let's see, we did step 1. We did step 2, we drew the airplane with its chord line. Okay, step 3, we're going to draw the velocity vector. Which direction is the airplane moving? It's not necessarily moving along the horizon. It may not be moving forward like that, directly along the chord line, and so it could be following this path. So draw velocity v infinity there. Actually, let's call it v. And then you draw the relative wind coming in the opposite direction. Yeah, because it's if the airplane's moving through the atmosphere this way, then if you're sitting on the airplane, you see the air coming in the other, exactly opposite direction, parallel. And then this thing here, this angle, label it as alpha because that's the angle of attack, right? It's the angle of the wing to the relative wind coming in. And again, the relative wind is opposite the velocity of the center of gravity because the air is still, the CG is moving in that direction. Okay, so we did that. Label this angle theta. And I'm going to start listing these. So alpha is the angle of attack. And theta is what's called the aircraft flight path angle. And why is that? It's because if the velocity vector is going that way, then if you traced out the path that the CG traces, it's going to follow that line. If you looked at where it goes in time, it follows the velocity vector. It has to. And so that's the path. If we follow that, we get the path of the airplane as it goes through the air. Okay, we got that. And now we need to put let's see, that's 6. Let's put the weight on. So the weight goes straight down. So the weight is perpendicular to the horizon. Because that's the way weight works. It goes toward the center of the Earth. Earth's such a big radius that you can almost draw a straight line that represents the surface of the Earth. Okay, so we got that. Now let's draw the lift. Weight is perpendicular to horizon. Which way do we draw the lift? By definition. This is one of the most important things that you can memorize for your career. Yeah, that's key. It's not perpendicular to the chord line or the horizon. We define it. I mean, you could, if you wanted to start your own airplane company, define it any way you want. But the way everybody throughout history and all of the data, oh, somebody joined in and I didn't get it spotlighted. There we go. So is everybody caught up? Drawing the picture? So lift, by definition, according to everybody that does it, so we can all use the same tables, is perpendicular to V or V infinity, because they're parallel to each other. Yeah.
What is the reasoning behind that? Does that make any calculations more convenient?
It's because if we're in level flight, where we want to fly parallel to the horizon, then our velocity is that way, right? So if I tilt this down so that theta is 0, flight path is that way, so we're in cruise. We've already climbed, now we're cruising. Then the weight is this way, and the lift, and so the lift counteracts the weight. That's why. Like I said, you can define it any way you want, but this makes sense. You go into a wind tunnel, you know the direction of the wind. Lift is perpendicular and drag is parallel. You're in cruise, that's what you want. Other conditions you have to take into account that then the lift is different angles. And in fact, look at this. Lift is not going to counteract weight if we're climbing. And we'll get to that, so hang on with that. Okay, and then drag is parallel to V infinity. or the velocity. Or you could say drag is perpendicular to the lift, because we're resolving the aerodynamic force into two orthogonal components. All right, what force am I missing? I got lift, I got weight, I got drag. Is there anything missing? Thrust, yeah. So we're going to draw thrust, and we're going to give it its own angle. So draw it like this. Label it T. And we're going to call this alpha T. We could call it anything we want, but it's the angle of the thrust line relative to the velocity vector. Now, when we get into 514, we'll define that more carefully relative to the geometry of the wing, but for this class, it's convenient to just do this. So let's list it here. Alpha T is the angle of the thrust relative to the infinity. And again, that makes sense if you consider cruise, because typically if you're in cruise, you want the thrust to counteract exactly the drag. You don't necessarily want any thrust to help lift the airplane because it's not efficient. All right, now I need to tell you something that you need to forget for 3 months and then remember suddenly in January when you take 514. Most books on flight dynamics, including the 514 book, labeled this as theta, and they call it the pitch angle, because it's the angle that the airplane is pitched up relative to the horizon. And then they call this gamma. And that's the flight path angle. Does the red show up? Yeah. When you look at the screen? Okay. So in this book, theta is the flight path angle. Almost every other book in the world, gamma is the flight path angle and theta is the pitch angle. Now, I think he did that in this book to keep it simple because everybody works with theta, right? Sines and cosines of theta. And it's okay as long as you just remember that theta is the flight path angle in this textbook. So the red stuff we will never use in this class. So everybody raise your right hand and say, I solemnly swear to not remember gamma until January. All right.
All right. In space dynamics, they use gamma for flight path angle of spacecraft as well.
Yeah, and in there you'd find what you do Euler angles, and we'll get to those in 514. And theta is one of the Euler angles for airplanes, but with the spacecraft, I forget, there's different names and different symbols used for the orientation of the aircraft. Okay, so everybody got this. This is our free body diagram for our flight. Now, how are we doing on time? 4 minutes. Breaking news, NASA discovers water on the moon's surface. Sorry, I just got an alert. And it was relevant to this class, otherwise I wouldn't read it to you. All right, so the directions that we're going to do the force balance, Newton's laws, are perpendicular and parallel to the flight path because lift is perpendicular, drag is parallel, and that makes it all easy. And so I need to borrow some space here. I'm going to add on But I want to leave the diagram here so that we can do the equations. All right, so the sum of the forces parallel to V infinity change the magnitude of the velocity vector. Either speeds the airplane up or it slows it down, right? If thrust is right along the velocity vector and drags that way, if you have more thrust than drag, then you speed up. If you have less thrust than drag, you slow down. So some of the forces perpendicular to V infinity, what do they do? Change the angle. Change which angle? Yeah, exactly. Because it causes curved motion, right? If you have a ball and it's moving this way, to make it curve, you have to have a force perpendicular to the motion. And so this changes the direction of the velocity vector. And we all know Newton's law, sum of the forces parallel equals mass times acceleration. Sum of the forces perpendicular equals the velocity squared over the radius of curvature times the mass. Okay, so let's do these and then we'll be done for today. So sum of the forces, which one do I do first? Parallel. We've got, so we're going this way. T cosine alpha t minus drag. I erased drag, let's put it back in. See how that makes it nice? Drag is parallel to V infinity, so we don't need sines and cosines for it. And then we got the weight. What's this angle? We got to do components of the weight this way and this way, right? And this is that angle theta. So we got to get perpendicular and parallel components. So this is W sine theta, right? The opposite. There's our sum of the forces parallel. And then the sum of the forces perpendicular is just the opposite. So we get lift minus W cosine theta. So now we're getting this component here. And then we got a little bit of thrust. And these are our equations of motion. And we need to set what they're equal to in terms of Newton's laws. So I'm going to erase now that we've used this. Sum of the forces parallel, speeds up, it accelerates. So mass dv by dt, mass times acceleration, and then perpendicular is mass velocity squared over the radius of curvature. We don't use that much, so let's just write it out, radius. Okay, so we'll start with these next time. Now, this is the most complicated case. We'll specialize it for level flight, where we tip down and theta is 0. That's going to knock out some terms, right? Make them easier. And then we'll kick in climb. So before we leave, notice that if you look at just the picture, forget the equations, I've drawn this as climbing at an angle theta, right? So a component of the weight actually opposes the thrust. So to climb, we need more thrust than if we're just in level flight. From an energy standpoint, it makes sense, right? If you're climbing, you're gaining potential energy. So you either lose kinetic energy or you have to add energy in via thrust. So you need more thrust than drag to climb. And that will tell us how fast the airplane can climb and in fact how high it can climb. So we'll get into that next time. All right, I think we're done for today. Thanks. Hopefully you guys stay safe driving. Roads are not too bad, but I think they might get worse tomorrow.
Where's the enemy squared where R from?
This is just the centripetal force required to do a turn of radius r. It's part of Newton's laws. If you go back to dynamics and you study circular motion.
Yeah, I remember like V squared over R. So
Yeah,
like the acceleration of a circle or whatever.
yeah. So if you have a ball on the end of a string, I don't think it's anything anybody ever derived. If there's a fundamental way, it's just experimentally, Newton determined that. But if you have a ball at the end of a string, for it to follow a curved path of radius r, you need that much force on the string toward the center of the turn.